All right, everyone. Welcome to another episode of Robo Papers. We have here Roger Chiu. Very happy to have him sharing with us his latest paper, Humanoid Policy, Human Policy. Glad to have you, Roger.
Yep. So thanks for having me. I'm Michael and Chris.
Maybe as a start, if you can share a little bit about yourself, how do you get into the space in the first place?
Sure. So I'm currently a first year PhD student at UCSD. I work with Professor Xiaolong Wang. Before I joined UCSD, I actually spent a few years for my bachelor's and master's degree at the University of Illinois. So yeah, so when I kind of beginning as when I began like my undergrad study, I was actually like a math major, and I spent like 1 year to figure out okay, like I maybe I like something that when I works it out, I can see it, I can feel how it's working in the real world than math. So I kind of switched to working on more like the robot sides when I was a sophomore. Yeah, that's when I kind of began to do like robotics projects, and then a little bit kind of research, and then deeper and deeper into research. So yeah, this is like an overview of our projects on humanoid policy, human policy. Yeah. So one of like the motivations for this project is on a recent success in like cross embodiment learning, and so that's where I think a lot of recent papers are working on is to try to train like a generalist policy with diverse like cross embodiment data. And what they found is that doing such training actually improves like generalizability. But one question that we had was okay, so we have this cross embodiment learning, which is good. It tries to kind of aggregate all existing robot data, but where do we go look more like for the where do we go to look for more data? And what we did was we look at like what happens during like the robot data collection. So this is actually like a video from the open television that Chris and Michael, you guys tried at Coral. So it's like a kind of like a VR teleoperating robot. So I have like one of our lab mates, she's in here, is trying to teleoperate this like humanoid robot. And what we found is in robot data collections, we usually have like a teleoperator doing some sort of human motion. And then with some retargeting, it can be either like VR device, it can be like joint copies, but there's going to be some mechanism that copies or retargets this action to robot actions. And this is what happens behind the scene for robot data collection.
Could you talk a little bit about why we need to do retargeting?
Yeah. So for like retargeting, because when like robots and like even like for humanoids and humans, we don't have exactly like the same configurations, right? So what we do is in VR, like a teleoperation is usually like tracking, for example, like the wrist, 6 wrist poses of the human operators and translates that into robot motions. And this like translation is usually done via, for example, like inverse kinematics. And that's what I meant by retargeting. Yeah. So with this, what we thought is, what if we remove these layers of interaction? Like, what if we don't do this like inverse kinematics, but rather directly like collect data from humans? So this is like an examples of the like a grasping task from our paper. So we have like both humanoids and the humans doing the same, like a similar task, like grasping the bottle, like right in front of the, right in front of them and put it in a basket, like a bin before them. And this is like a humanoid completing the same motion. And what we thought is with this kind of what we call like a task-oriented human data, can they be directly used as a like a source of for like cross embodiment training? And if we like look at the like a histories of this like learning from human, it's actually I think not a very like novel topic in both like computer vision and robotics. I think there has been many people who try to do design methods or like data sets to learn the methods or models to learn directly like from internet human videos, because it's like a very scalable source of data, like human data. But I think existing work, they have to design some sort of like surrogates, like segmentations or affordance to as a kind of like a proxy to learn from this like internet human videos. And what we propose in this paper is kind of like something in between robot data that is directly aligned with robot and internet human videos. And that's what we call like this data, what we call like task-oriented human data. So compared to robot data, it's collected without a robot, like this task-oriented human data. But compared to internet human videos, they are not just, some like recordings of people doing some random daily tasks. It's recordings, like egocentric recordings of humans doing specifically like the tasks that is directly aligned with what we want the humanoid to do, with clear start and markers of the recording episodes, and with good the annotations of the hand and finger poses.
So just to be clear, so what you want to do for what do we want to train? What do we want to actually predict here? So you have the human data. You have human data of like the task you were just showing was picking up a bottle and putting it in the basket. And there, so I have that, and I have my 3D hand tracking that shows exactly where the human hand is, and then it is doing inverse kinematics, but it's predicting what is the retargeting? What needs to change here? What needs to be retargeted?
Yeah. So if I actually go to, for example, like this slide.
If we're gonna get to it, it's okay. You can just like we don't need to jump ahead. Yeah.
I think I can like kind of give a little glimpse into what we do. So what we like ends up doing is having like a model architecture that is essentially agnostic of the embodiment that it's dealing with. Like we don't explicitly tell our models like if it's dealing with humans or humanoid. We have a unify like what we call like a human centric representation that we use for like both the states and like as inputs, state inputs to the policy, and also the prediction kind of like an output action space. So the policy, it has zero knowledge of actually any like inverse kinematics and retargeting. We hide these procedures in data processing and the deployment script.
So okay. So it's not doing inverse kinematics. I'm just predicting like kind of like the qualities of where the hand is in 3D space.
Policy learning is like not doing any inverse kinematics. Yeah.
So why do I need to do transfer then? Like if I know where the wrist is, I know these finger positions. Why can't I just do inverse kinematics?
I think inverse kinematics also works. Like retargeting, that's just for like a smoother, for example, like a finger actions.
Gotcha. Okay.
Yes.
And that, of course, is extremely important when it comes to like dexterous manipulation. So you can't just
exactly. Yeah. So if I go back here, so with this like the data we collected, we actually like as you can see, like we work with like Apple, some people from Apple as a kind of like external collaborators for these projects, and we ended up like collecting I think a very large scale like a data set. So we call it like a physical humanoid data, and it's task oriented, as I said. And by task oriented, it means it's directly aligned with the task. It has 3D annotations, and we try to basically like diversify like a lot of factors in this data collections, because there's like, for example, like there are actually still gaps between human data and robot data. There is, for example, like different heights of the teleoperator. Got like a basketball player in our lab who also like helped collected like some data, and that guy is like super tall. And we get like people with different length of arms. We get like different heights of the table and distance between the operators and the table, objects, receptacle, like or backgrounds. We try to randomize a lot of factors in this like data collections. And we ended up like having like a human data with I think roughly like 30,000 demonstrations and over and nearly I think 4 million frames collected in 30 Hertz.
Ton of data.
Roger, can I just jump in and ask a little bit about this, the human side? So this nearly 30,000 demonstrations. So I suppose you hire some volunteer, or maybe you guys yourself did it. How long are we talking about here? Like how many man hours? How many people are actually involved? And does the person need any specialized skill, or literally is anyone can do it?
That's actually a good question, and that's I think some good things that we found about like human data here. So first of all, there isn't any like specialized skills. Like it's like different from like teleoperating robots. from my experience, like teleoperating robots, it actually takes some time to train the teleoperators to get to know, for example, like get familiar with the singularities of arm.
Yeah.
But
Yeah.
here in human demonstrations, there isn't like we don't have like such training. We just have like instructions on, for example, how to like randomize objects, how to, for example, like start and end the recording. But there is no such thing as, like training someone to grab something and put it back somewhere. I think we all had the same training when we were babies. So yeah, and in terms of like man hours, it's actually not that much. I think roughly the data here translate to I think about like 24 ish, like 20 to 25 hours. Like I don't have like that number off the top of my head now, but it's like roughly that level. And to collect this, like say like 25 hours of data actually just take I think 30 to 35 like man hours, and that's it. I think it's pretty doable. We are actually like have again like a follow-up this project. We are still kind of continuing collecting human data on our end, and there is me and there's some like other volunteers in the lab, and there's another student working on the project. Spend like 1 hour maybe for both persons to collect like data each day. Like a week we generate like basically like 10 hours of data. So it's like really not that hard because it doesn't require a robot.
Yeah, so like 30 hours of work for 20 to 24 hours of data means a pretty high retention rate, which means that all the data is actually fairly useful, which is actually not always true for demonstrations and teleop, I think. In my experience, that's a pretty high rate, right? I would say. Also, that means that all the tasks, if you've got 30,000 demonstrations, are very short, right? Like these are like, they're all like atomic skills, like pick up a bottle or kind of stuff.
Yes, exactly. And I guess one other thing is that like you can see from the numbers here, there had like the average length, like the average frames in a demonstration for human and robot is actually much higher than humans because it's hard to teleoperate like human and robot to do something. It's not I guess hard in terms of successfulness. It's hard in terms of efficiency. Like I can do, for example, like a glass pick and place in 10, 15 seconds on a human or robot, but when I do like this human data collection, it takes like 2 seconds for me. Yeah. So yeah, with this, so this is like an illustrations of some data we had in the data sets. And yeah, to do this like data collection, we actually like spend a lot of time on it. So the first iteration we had is the setup with like the red boxes and red circles here. So it's essentially like the kind of open television code, like a videos that I just shared. It's based on that. And what we did is that we simply like attach the cameras that was originally on the robot to like the VR device. But what we found that is it's both heavy, like the VR devices are already heavy. Having like an additional camera is even heavier. And it also requires some sort of compute to be connected to the camera to do the recording. So what we end up doing is we actually wrote like a Vision OS app for like the Vision Pro. So we have this like native app that has access to like one of the cameras on the like the Vision Pro's camera arrays. And our app uses the AR kit to collect the head and hand poses and also do the kind of like video recording from one of the cameras. And we do data collection with it. So doing
Curious,
that. Yeah.
Sorry, Roger. I'm curious. Did you find any difference between AR Kit from Apple and WebXL from Meta? I guess both the SDK, but also like the hardware itself. I mean, obviously one is maybe 10 times the cost of the other. Is there any trade-off when you use Quest 3?
Yeah, there is actually, the answer is actually yes. So for Meta Quest, we found like the hand poses are actually a little bit like jerkier when there's like occlusion. So for example, when I'm like holding like a bottle of water like this, and from the views of like the VR device, my like 4 fingers are actually like, not visible in their cameras. And in this case, the like a fingertip predictions from Quest is actually kind of start to kind of jitter a little bit, which is like not ideal. So we ended up doing, I think, a lot of like collections using the Apple Vision Pro. And also by the time when we kind of started developing the app, there wasn't any kind of open APIs for the Quest side to get access to the cameras in their app. I think they opened up like the API access like very recently, but there is no API to get video recording back in last year for Quest.
Got it. But I think both sounds like a software is something that can be fixed by software, not so much the limitation of Quest itself. Would you say so? I mean, the occlusion. It sounds like something that if they work harder on the SDK, they may be able to do that inference.
There's also like the onboard compute and the camera. The camera resolution is different, I think, between the two. I wonder how much of a difference that makes.
Yeah, at least like
Cool.
we actually try some like off the shelf visual models to like inference, like for example like finger poses. I think they don't work that well with like the egocentric visual observations. So I assume that I think both have some sort of like proprietary models to do that predictions, and it's actually not that trivial to solve, even it's a software issue.
Yeah, it's interesting to me that you brought up this point. It's like having an entire team of like, I guess you meant Apple engineers like refine poses for you, because there was another paper.
All the SDKs to do the like the finger.
Yeah, there was another paper, and then in another episode, I think Bahir, right, like really lean into using iPhone and the AR kit that just out of the box and just solve so many of these like very precise engineering stuff out of the way.
That was
Make the
basically it
research a lot.
solves your SLAM problems too, which I think it's nice.
Yeah.
Seems like a great. And honestly, the $3,000 or whatever that an Apple Vision Pro is nothing compared to a humanoid robot. So it seems like
Exactly.
There seems to be like a general trend to use this like AR kit things like more and more in research. I remember there was also like a paper from Stanford last year. They like mounted an iPhone on like one of the robot dogs to do this SLAM with localization, and they found it to be like super accurate.
yeah. There's a few. I remember seeing a few results where they compare the iPhone SLAM to like a bunch of other methods, and it just beats a lot of off-the-shelf open source stuff. It's impressively good, actually. And of course, now there's like people putting the Meta glasses on robots and having them do stuff. So yeah, we should keep going though. This is a tangent.
Yeah, I mean it's casually. We're just casually chatting.
Yeah.
All right. So this is some examples of what we do with like in the wild data collection, because with the like the Vision OS app that I just described, the data collection does not only not require like a robot, it doesn't require a computer as well. So all we need to do is like carry a portable VR device, and we can do like this data collection anywhere. So I have here like doing data collection in an outdoor environment. This is like doing some like pouring in the restaurants, and this is doing some again like some object pickings in one of like the bubble tea shop, like a local bubble tea shop.
So you can very easily get a very wide diversity of
Sorry, Chris. Sorry, Roger, I was going to ask, so all these tasks that you define for this paper, are they like more just manipulation data in the same spot, or are they mobile manipulation? That means like the human, do they move around?
Yeah, that's a very good question. So right now we are not doing like a mobile manipulation, but that's something that we are looking into. Because I mean the kind of like a rationale that why we did it was we wanted to have like a good version, as like Chris suggested, like some like a good atomic skills for like humanoid robot. Like we can have like generalist policy on that with this atomic skills without having too many potentially confounding factors like mobile manipulations or just like a whole body movement. But we are definitely thinking about extending this kind of like a framework into doing like, for example, mobile manipulations or like whole body manipulation.
Yeah, I mean, another thing that I like about this, so you're showing this in a lot of different environments. This is something that showed up in a couple other the chats we've had, right? Like, and a lot of the other literature recently is like, to scale robot data, we need like a really wide diversity, and it's very hard to do that of data, and it's still very hard to get that with a humanoid robot. So it's something nice to see here. So how many environments did you end up collecting data in?
That's a very good question. I think we actually didn't keep a track of that, but it's like super diverse, I think. At least like dozens of. I don't have a precise number though. Because I mean, because it's like easy to do data collection,
It's
right?
so easy, you don't even need to think about
Oh
it. That's
yeah,
nice. All right.
like
Yeah.
so it's, we didn't even keep it. But I think in terms of like the data that we have released right now, it's around I think 30-ish scenes. We actually have like some data that we are kind of still working out on the licensing, but on the release one, it's around 30. But it's like again, it's like super easy. So I think the numbers of scenes doesn't make that much sense now because it's like literally just taking like adding like a new scene is literally taking the VR device and some objects and do manipulation. It can be done in like 5-10 minutes.
Nice. Sorry, is this, and this is not language condition skills. This is like labeled after the fact. You just like write up what you did, or how do you do it? I guess.
So we actually like do collect like language instructions for each task. So the way that we are doing it is like we are organizing tasks like this collection in terms of sets. And in each set, we have like a language instruction that the operator needs to like write before they start doing the when a set of recording begins, they do this like data collections begin and stop recording, reset the scenes, and potentially like randomize some, for example, like locations of objects and receptacle, and do start recording again. But essentially, it's like same language instruction for each set, and within each set, we randomize object placement and receptacle placement.
Did you have to do anything special to like consider that when you're taking this to a new environment, like all the randomizations, or is it just like naturally fairly easy to get a good diversity of configurations? I guess.
Yeah, we actually do need to consider that. Like we found that with this like a human data collection, it's actually easy to get a very diverse backgrounds, diverse environments. But in terms of, for example, like the placements of the objects and the like the selections of object, placement of the objects, it still I think takes some efforts.
Kind of makes sense. People just tend to place objects at comfortable positions to
Yeah,
grasp, so you end up with a fairly
and
yeah.
it's gonna like introduce some bias in the data set. So we have like explicit rules to like tell all the like the operators to like not do that, to try to randomize as much as possible.
Gotcha. Nice.
Yeah, for like the model, so that's enough for like the data kind of like efforts that we had. So when it comes to like the model method designs, we start with like looking at the sorry. Yeah. So yeah, it starts with looking at the robot observations and human observations in both scenes. And you can see here that we have egocentric visual observations for both like the robots and human settings. And we also have like these key points. So these key points are what we use for like both the policy inputs and outputs. We try to like keep it the same for like both the robots and the humans to represent their emotions using the hand key points and head rotations. So you can see how this like key points and you can see how the hand key points move in the trajectory as the trajectory goes. Yep. And for like the model design, we take in like the robot observation and human observations. So for like the robot observation, the pipeline is similar to like a tally operation. We simply have like a human tally operator to do some sort of actions, which is then like translated to humanoid actions. During the data pre-processing, we actually do forward kinematics to again translate the humanoid actions into wrist poses and hand key points, which to make it consistent with what we call like the human-centric representation. And for the human demonstrations, because they already come in the forms of wrist poses and hand key points, there is like no forward inverse kinematics needed. But what we found necessary is to do kind of like a slowing down. As I said, like grasping, for example, in the grasping task, humans are much more efficient than robots in grasping and placing some objects. And what we found is there needs to be some sort of like a slowdown factor in this case, in which case like we do like computed like some statistics of this like of the ratio between like the average task completion time. And what we found is like a distribution that is like centered around 4. It's like 3.8-ish for like grasping, and it's like 4 point something for pouring task. And we ended up using like a constant like a 4 to slow down all the human demonstrations by 4 times during the training.
That's interesting.
Um,
Always, so 4 times always works, or what happens if you don't do that?
If Yeah, we actually also kind of like out of my curiosity, I did try that. And what happens is like the humanoid robot started to move at a speed that I think is somewhere in between the humanoid demonstrations and the human demonstrations. And because I think it's moving faster than what our I think the retargeting algorithms and can handle, the actions were a little bit like unstable.
Gotcha.
So yeah, it wasn't. So it didn't have, I think, a very good manipulation success
Yeah.
rate.
So like I'm curious if you could like train it at full human speed and get it to, or like speed up the robot trajectories or something and then slow it down during execution, or I don't know if there's a way to make it run faster in your mind. Yeah.
Yeah, there's definitely a way. I think we can do some like similar sampling, for example, like in the predicted actions to, like either make it go faster or make it go slower. I think Figure AI actually does similar things in their like Helix model.
Looked
Yeah,
at that.
Yeah, they did. I think like a 20% speed up in their like sampling of the predicted actions. Yep. So yeah, going back to like the modeling. So once we have like all the states here in the like the as the policy inputs, as I said, like the models, it takes in the current egocentric visual observation, takes in this human-centric risk poses and hand key points, and it predicts a trajectories of future risk poses and hand key points. Also, because the head of our robot is actuated, so it predicts like an additional actions of the head rotations.
I don't think we have which robot. It's the H1.
Yeah, H1. I actually
H1,
have a image here on the
H1.
yeah. It's H1, but we have this like a customized head. It has like 2 dynamical motors on the head that I think actuates it. So the head's kind of like its next turn. Right? Yeah.
And I read that in your paper you kind of asked the human demonstrator to not move the body too much. Is it related to the fact that basically the robot can't move and also the head is kind of fixed?
Yeah, it's related to how we are deploying like the policy to the robot. So as I said, like, though we are like definitely looking into doing, for example, like mobile or whole body things in our like follow-up steps. But for this like version, we try to keep these confounding factors away, and we are not doing any like whole body motions of the upper body of the robot. So if like the collected data ends up having some sort of like this like an autonomous movements of person, like someone reaching for an object, leaning kind of like leaning forward to reach an object, the robot has like no way to do that motions in at least in the current deployment setup. So yeah, with that, and yeah, we did like a quantitative evaluations on like several different manipulation tasks, and yeah, what we found is for in distribution settings, that refers to scene setups that is presented in both the robot data and human data. There isn't much difference between policies trained with robot data and policies trained with human data. But when it comes to like out of distribution settings, which is referring to scene setups that is presented in human data but not robot data, the policy co-trained with both the robots and human data has a much higher success rate in these settings. And yes, also like this data also helps with what we call like a cross-humanoid deployment. So we work with like CMU people to deploy to train policies on their ends. And what they did is they collected, I think, just around like 20 demonstrations of humanoid, like grasping and placing some objects. And what they found is when the policy is just trained with this like 20 demonstrations, it basically fails every time because I think 20 demonstrations is like too few to train anything that's useful. But when it's combined with like a mixtures of like our data, even with just like 20 demonstration on the target embodiment, like the robot is still able to grasp like a variety of objects.
This is very useful. Is that the same humanoid? The head looks the same as yours, but it's a different humanoid. Or is
Yeah,
that
the head is, I think is the same because they also wanted to have some sort of actuated hand. It's also H1, but it's like a slightly different model. So if you look at like the arms, it's actually two different arms.
Okay, yeah, because it looks slightly different from yours. Okay, that makes sense. The head's not moving much during this, though. You said it is actuated and tracked. Is that just like big partly due to the atomic nature of the skills, or what? What is that? What's that?
I think it depends on like the skills because for grasping, there doesn't require like too much movement, right? For grasping, you just do this and place it in some sort of bins. But
Yeah.
when it comes to pouring, I think which I have examples in the next few slides, the head does move, like left and right when it does like different manipulations. So
Especially for passing. Good passing is passing back and forth, right? Yeah.
yeah, so yeah, this is showing some like object placement generalization. So we intentionally like included only like a few training demonstrations of the robot picking objects from the left here. And that's how like this robot only policy fails because majority of the training data is picking up this like little box from the right hand side. And but in contrast for this like coaching policy, despite it doesn't contain like it contains like only few demonstrations for picking on the left. Because the human data it was trained on has a much diverse object placement distributions, it's able to like picking up this box from the left in just a single trial. And yeah, this is like a cut passing. I think there should be some. Let me see. Yeah. So again, let me do some explanations here. So in this settings that we collect like robot data just in this settings, like passing the cup between both hands on this like colored papers. And then we try to like roll out the policy in like different backgrounds. And what we found was the robot only policy, because it has only like seen these settings in its like the training data, it doesn't work well. Like it does this kind of like passing for like 1 or 2 turns and then it kind of stops and failed completely. But for like the policy that is co-trained with both the robots and human data, it works even the robot has like not seen these different like backgrounds in its like training robot data. So yeah.
And this is again, these different backgrounds that it's been trained on are the really diverse environments. So these are all videos from the lab, but like you have it trained on like all these different tables. So right here, yeah, lots of different environments and lighting conditions. Okay.
And yeah, finally I have this like a slightly more long horizon, like a pouring example. So that's where you can like see, I think, the head movements. For example, like when it's like grasping something, you can see like its head is like looking at the bottle, and then when it's grasping the cup, it turns left a little bit to look at like the cups and do this grasping operations and put it back. So again, like in this case, we put down like this visual markers here just for kind of a clarity so that it's like more visible. So this is like from the training data. So in training robot data, again, like we try to like keep this bottles and the cups in like this like straight lines. And then during like the evaluations, it's somewhat like an order distribution settings where they're like their locations are like more randomized.
So the markers are the cups on the left in the training distribution are all in like on these colorful coasters that are all just right lined up in the front of the robot. That's what you're talking about when you say markers.
Yes,
Yeah.
that's why. Yeah. So
Yeah.
illustrating like how this plays like differently from the training set.
Yeah.
Yeah. So yeah, so I think that's the results in our current version of the paper. But it's like we are still kind of looking on follow-up things that we can do. So I think what we have shown in the current version is that human data can improve various like generalization. I think this is consistent with findings in existing literatures in cross-embodiment learning. And what we are looking to do next step is we are trying to design what we term like an egocentric generalist policy. So compared to like existing policy, we think it makes sense to try something without relying on like an external third person camera. Like the policy should take in just like egocentric views and it actuates the robots. And that's it. Like there's no need for like an third person camera. It's like this egocentric, I think it's also similar to what Figure AI is doing. And it's also consistent with our human data collection procedure because we are getting.
Yeah. So sorry, egocentric. You are doing egocentric data, right? All this data is from the robot embodiment. So what you're saying is novel is not the egocentric part. It's the generalist part. It's it. Right now, they're atomic skills. Just to be clear, right?
Yes, exactly.
Oh,
so yeah, that's right. So we are working towards like this, like a generalist policy that with egocentric atomic skills, and we wanted to work on like many different robot embodiments. So yeah, that's kind of what we are looking at. And another like questions that I also get asked a lot after like this kind of like I put we released this paper was like, will simple scaling of like human data solve all the problems? I think the short answer is I think probably no. But I think like the human data is, I think still going to be like a very useful data source for like training based model. So if we look at like the current paradigm, for example, for like Pi Zero, how they are like using all the data and how they are doing like complex tasks, it's like divided into like two separate stage. So in the first stage, they do some sort of like a pre-training of a base model to adapt, for example, like existing VLMs to add, for example, like a action expert to allows it to make predictions on a variety of tasks. And then for like more complex downstream task on, for example, like a specific robot embodiment, how people are making use of this base model is they collect data from target embodiment on specific task and they do sort of some sort of like fine tuning so that it's with the help of like the better initialization from the base model, even with the same amounts of like fine-tuning data, the version that is fine-tuned from the base model would behave like much smarter than something that is trained from scratch. And in this case, we think that human data can be like a very important player, can be a very important data source in pre-training egocentric generalist policy.
So have you tried anything like this? Like train your generalist policy on, or train, I guess, like your pouring task and then fine tune to try to get it to solve the passing task or something like that?
Yeah, that's actually like something that we are working on right now. So as you see, we actually have some preliminary results on that when we do this like a cross humanoid deployment example. So right now we are trying to do this and also like scaling up the training scales because as I said, like when we do like this data collection, we actually have like this like a instructions accompanying like each training demonstrations. So we are, I think, looking at training like a language condition egocentric generalist policy right now.
Yeah, Roger, I'm curious. Like, did you explore checking out like some of the other like egocentric data sets, Ego 4D? I think there's an Ego Kitchen. There are a bunch of these. Why do you think it was necessary for you to kind of collect a separate one? Like, what's the pros and cons? Or do you think you can actually also take those existing ones?
Yeah. So I think that's like one of the thing that I mentioned when I kind of put the like the data pyramid figure, I think a few slides ago. So I think Ego 4D, Ego Kitchen, those data set, I think actually falls into more like the categories of daily internet human videos. And I think those videos, they are useful for example, like training like a VLM, but these data are not that easy to use for like pre-training a base model. So we do have like some explorations projects in our lab to try to like, for example, like pre-train manipulation policy using like an Ego 4D in a similar manners, and then like doing some fine tuning on top of that. And I think the improvement we got from that was, I think, very marginal. So our like reasoning was like doing like the Eagle 4D is too misaligned with the robot data. I think we are, because I think we are like yet to get to that stage where we can have like a robot completing, like daily tasks to continuously work for an hour to complete like some daily task. Like, so that's what the video segments from existing egocentric data sets are doing. I think my take is like we do this in a kind of like a one step at a time. We solve from a bottom up approach. Like we look at like this atomic scale first, try to get a good models that can do atomic scales for different robots. And then we look at, for example, composing these atomic scales to do like more longer horizon task and ultimately make them to be able to do, like continuously for work for an hour to do useful household tasks.
Yeah, got it. I think that makes a lot of sense. This bottom up thing. Regarding so let's say for each individual task in your current data set, do the human just do it once or do it multiple times? How many demonstration with each task are you getting the human to do in the same environment and same scene?
Yeah. So if for like the same environment, same scene, I think it's usually 50 to 100 demonstration per set of objects. We do, for example, for one object, for example, for like the grasping task. So we do, for example, 50 demonstrations, randomized object placement, and then another set with, for example, like a new object, and then we do another 50 sets of 50
I
demonstrations.
see. Do you pick that number because you think that is the constraint of your data collection budget, so-called, like your 24 hours or 25 hours budget, man-hour budget?
I think
Or
it was. Yeah, that's a very good question. I think this, like the 50 demonstration, was more like a rule of thumbs that we kind of figure out. So initially we don't have like a specific number. We don't have like very specific guidance. But what we ended up finding was that doing more than like 50, for example, like 100 demonstrations per configuration, we end up having, I think, a bunch of repetitive data where the object placements and, these factors are too similar. And if we do like less than 50, I think if we do like less than 50, the randomizations of like the object placements tend to be like not enough. And besides, I think many like operators, including me, I find that like 50 is a good trade-off to get a little bit kind of rest in between.
yeah, there are only so many times you can pass the same object left to right, right to left, left to right.
Yeah, exactly.
Got it. Okay, that makes sense. Cool.
So
Yeah.
I guess this is like the last thing. So yeah, as I said, like this, like the human policy thing is like just a beginning. We have found that like it's useful in, for example, like cross embodiment learning, and we are trying to kind of we will be exploring the other kind of use cases for this. Like base model, that's something that I kind of already talked about. Dexterity, I think that's also like one question I get. So dexterity is something like, what doing this kind of like egocentric manipulation with some more like dexterous tasks that is more dexterous than, just grasping something. For example, like spinning or like in-hand rotations of objects, and also like learning like what we call like a slow system. So for example, like having the model look at the, like a long horizon, like a sequence of different manipulations, and try to, for example, command the base model to send out different language instruction to do like longer horizon tasks. And one other thing is, I think our data is also like not limited to, for example, doing this like an end-to-end learning for manipulation policy. If like someone wants to use this like a task-oriented human data to learn some sort of like affordance model to design like a manipulation policy in a like a modular fashion, I think our task-oriented human data is also like compatible with that. So I do think like there's like a task egocentric human data will play like more and more important role. And I think also, for example, like Meta also thinks the same, that they are like designing this like a project area glass, and I think it will be like much easier to use than Vision Pro. I mean, after all, it's lighter. And I think recently, like the Project Aria 2, like the Gen 2 came out. So I think that's also like a one hardware that we are looking at to, like to collect more like a egocentric human data.
I definitely like the idea of using these to scale this data collection. I am really curious if it's good enough to do like in-hand manipulation though, like rotating an object in your hand. That's like seems like that would be like such an easy win because of how good the hand tracking can be. Although, is the hand tracking good enough for that actually on these things like the Vision Pro, or do you think it's not quite there?
I think it's not quite there.
Okay,
But
fair
I
enough
do
then.
think that if we want to do like some sort of like this in-hand or rotation thing, there's probably needs to be like some sort of like a low-level skill.
Yeah.
Yeah, so kind of like a low-level, like this like control skill that you probably get some, for example, RL in simulator, and then you have this like a higher
Kind of-
level, like a not so accurate key point tracking that tells the model like when to like invoke like specific skill and for example like configurations of the
That makes
objects.
sense.
Yeah.
Okay. Yeah. I was. Is that the same reason why it's not like you're not like actually handing one object to the other in your passing task? You're placing it down first. Is it also just tracking issues?
Well, that's actually not the case. We
Okay.
are doing like some like in-hand kind of a passing.
Oh, okay. Did I just
Yeah.
miss that in the videos? All right. Well, let's.
No, you didn't miss that. We just don't have that in like
Okay.
that in this version. Yeah.
Yeah.
Okay. Yeah, I think so. Yeah, that's it
Great.
for my slide. Yeah.
Well,
Yeah, that's really cool. Yeah, really really cool paper. I think I mean this human, I guess you call it human data, is way more scalable potentially than teleop. It's
Yeah.
easily at least 4x faster. In fact, you have to slow down the human X in order to accommodate the robot data.
As humans are, yeah, very good at manipulation, as you were saying earlier. Is
Yeah.
that what would you say is like the lead takeaway from this from you? Like if you're for someone else who's reading this, what do you think is the number one lesson?
Well, I'd say human data is useful, but random human videos from YouTube may not necessarily be that useful.
Okay. So good human data is useful, and you can get it from
Good
these
human
VR
data is
headsets.
useful.
Okay. Yeah. All right. That's okay. That's nice. Cool. All right. Well,
And just a double take on that point, it's not just the fact that YouTube video don't have depth like data. It's more also like, I think to what Roger was saying earlier, if I'm not wrong, that it needs to be specific to some task. It's task specific.
Yeah.
Egocentric data with the 3D information.
Mm-hmm. Yeah, task oriented. Yeah, task specific. Yeah, that's the thing. So yeah, my take is always I love to like work on things from like a bottom up manner. Getting like atomic skills work first, and then do something that is more like a complex, challenging, or longer horizon. So that is my take.
good.
Sorry, Roger. So if I just go and double take one more time on that one, what if from the huge archive of YouTube data, YouTube somehow gave you egocentric videos specific to the task that you were interested in? Let's say, vertical grasping. Would you
I think if there's
say
a
something
good-
different?
Yeah, I think if there's a good way to do like good retrieval and also like a good 3D annotations, I think they may prove like much more useful. But I think both of the two things are difficult right now. So as I said, I have like tried out a lot of things on like this estimating 3D hand poses from my like monocular videos, and I don't think like there is any very good like publicly available model that does that right now. And on the retrieval part, that part I'm not that sure, but I think if like there is a good way to do both, I think we may find like more use cases for those data.
Got it. Cool. So
makes sense.
retrieval and some kind of like 2D to 3D, basically hand pose.
Well, it
kind
also
of
needs to be
estimation.
accurate enough that you can get useful actions out of it,
Yeah.
right? Like, could you
Exactly.
could you download it
Mhm.
and like replay? Like, do you have something so that you can watch a YouTube video, extract key points, and then replay it even in simulation, right? And have it do something reasonable. That's a pretty tall ask, actually, because usually YouTube is not going to be framed to have like a consistent egocentric camera view or a good calibration as to where the head is relative to the hand. Like you can't, because it's framed to communicate. It's a different thing, right? Which I think is the real takeaway here, right? Or part of the takeaway here, part of why you need this task-oriented data, I would imagine, right?
Yeah, exactly.
Very cool. Well,
Yeah.
maybe one last question, Roger. Any like mind-blowing paper you read recently that you just want to give a shout out to?
That's a good one. So I think recently I looking at the Roboverse paper. Not sure if you guys have looked into that.
Yep.
So yeah,
Yeah,
so
that's
that's something
cool.
that tries to like unifies like all the simulators with like a uniform interface. It's like not directly related to the human policy topic that we discussed here, but that's something that came to my mind when you asked that.
Yeah, it would definitely make simulators a lot easier to use. That's not, yeah, cool. Thanks for the shout out. We'll take a look at that. Definitely take a look at that. Cool. Well, thanks for coming on. This is a lot of fun.
Yep.
Yeah, thank you so much,
Yeah.
Roger. All right, really appreciate it.
Yep. Thank you.
Okay.
There we go. Yeah, that's
Probably
good.
for
That's
you.
good. It's the noise is just pointless. But yeah, so there you can see we're controlling this device, and then steering the robot around. Presumably, it's easier. Oh yeah, there we go. So this is the actual teleop that he's talking about here, where you can see the robot in the background, and that's me like trying to poorly trying to teleop this robot. So I think you can see there's a few of these points that he brings up about how slow the human teleop is, and I was really struggling through a lot of this. I think we did eventually get the task done. This is only a what 4 minute long video, and the task I was trying to do was stacking these two cans on top of each other. I think, and there we go, almost. Anyway, point is, and I get it done at the end, and it took like 4 minutes there with one reset. So point is, actually fairly difficult to do, I would say, to get this stuff to work.
To be fair, that was to be fair, that demo was cross-border. I mean, you were dialing in from Munich to the robot, I think, in San Diego. So
that was in fact
it's,
pretty impressive that even worked at all, right? Like that's
that was really. But anyway, I mean, back to this paper. What do you think? What have you learned, Chris?
I think that the main takeaway here was that I think that you can use these commodity mixed reality headsets like the Vision Pro and the Quest to be able to collect a lot of human data, and that it helps with generalization. So this is a story that's come up a few times in these things that we've in these discussions that we've had, right? Is that the main thing for scaling robot learning, the most important thing is getting a good distribution of data, getting a diversity of data. Right? We talked about this with on several of the things that the papers that we've had so far, and so here he's able to get something like 30,000 demonstrations in 30 hours, which is a pretty impressive rate, right? Like that's enough that you could, right? It's a very, very large amount of data. So,
yeah, I guess I won't call it commodity device. I mean, Apple Vision Pro is like,
the Quest
nearly
is a commodity
4,000.
device. That's the Quest is cheap.
It is true.
It is. Now he did say the Quest wasn't quite as good, but the Vision Pro, yeah, and they'll come down in price too. But also we've got a humanoid robot. Like a Vision Pro is nothing compared to a Unitree H1, right? A Unitree H1's $150,000. Unitree G1 $75,000. Adding $3,000 onto that is not going to be a big deal. I don't know. Yeah, that's.
Yeah, I mean, I think that. Yeah, it seems to. I mean, you remember like the other episode when we have Mahir? He basically used iPhone, right? I wonder if the hand tracking is. I mean, obviously iPhone is a lot more readily available than Apple Vision Pro. You know, what if you just create a cheap like head mount, put your iPhone on near your near your forehead, just look down,
Yeah,
and then
just the hand tracking, just track your hands as you go and manipulate stuff that way. It's uh I mean, I think the
I
problem
wonder.
is that you actually do the method that they're using. I think you need quite good data, right? It's like it's one of
Mm,
the reasons why we can't just use
mm,
web data, right? Like you actually do need to get, and is the iPhone good enough? I don't know. Maybe if it's like held, if you
mm,
held it properly, but as soon as, but this is like, I think one thing that I was commenting on being surprised by was that they had 24 hours of video data for like 31 hours of human labor, right? And that's
mm,
actually pretty good because a lot of the time you end up throwing out a lot of data and you end up throwing, and there's
mm,
lots of time that goes into setup and resetting and so on,
mm,
right? So like, and you've got
mm,
to like, so there's like why that 31 hours of labor is actually a really important thing to note because usually if you say that you collected like 500 hours of video data, you did not spend 500 hours on labor, right? Like you spent like
mm.
thousands of
Yeah,
hours on labor.
yeah, for
Like,
10x that. Yeah.
yeah, and like so I was actually kind of surprised by that. And like I think that, and like people get better at this, right? But I think a lot of the time it's quite hard to get good data and or useful data. But I
Mm,
think, and my guess is that once you start using like a janky setup, like tying an iPhone to your face, you're gonna end up with a lot of
mm,
useless data, and you've got to filter
mm.
that out, right? Yeah, I don't know.
Yeah, and
That's just
I
my
really
guess,
like the
though.
way he
Yeah.
framed the whole thing as like just treating human as another embodiment. So it's in
Hmm.
on the same class as the robotic, I mean the humanoid, and then he does the inverse, you know, kinematic and then a forward kinematic thing for the robots, and
Hmm.
obviously human already it's is already so both human and also robot are already in the same state space, same representation, and then therefore it's
Right.
just a single policy.
Because yeah.
And
Hmm.
yeah, um, yeah, and I guess like once you have that, then you can just use a lot of human data and probably don't need that much robotic data, and then you probably get something that kind of work already.
Yeah.
Uh, yeah, I think one question I wish I asked him just now was like will the performance been a little bit better if he spent a bit more time on the robot data side of things? You know, uh, that means he tally up a little bit more, maybe let's say double. I mean, clearly the human
Well,
data will
I
be
mean,
drastically
yeah.
more.
I mean, I think the teleop data, like, I feel like if you could swap in robot data for humanoid data, it's always going to be, or sorry, human data for robot data. If you turn human trajectories into robot trajectories and have robot data instead, it's always going to be better, right? Like, there's like no advantage to human data
Mm,
other than diversity and the fact that it's so much faster to collect large amounts of it. So like,
mm,
I do think
mm, mm, mm.
I have to imagine the answer to that is a hard yes. Like, it is going to be better with extra robot data, right?
Got it. Yeah.
Um,
So what human data gives you is that diversity, like because all the our distribution, you know,
yeah.
success rate are a lot better. One, yeah, I mean, when it's in distribution, it doesn't work that much. But so clearly, the human data brings in all the different environments, all the scenes,
Right.
because it's
Yeah.
you can be so much more efficient in the data collection process, such that you can afford to have a lot of like variety.
Yeah. Right.
Um, yeah, I
Because
think
like
that's the
so
appealing
so
part
this
about.
also does imply this is like a transitional data set, right? Like tool, right? Because at some point, if you have a lot of robots out there in the world, like I mean,
Mm,
clearly, like
mm,
if you could just get 30,000 human trajectory or robot trajectories, I feel like those are going to be
mm,
much more directly applicable to the robot. I mean, there is the general fact that perhaps the fact that humans, so it is interesting that the humans all have different like kinematics. So like the points on the hand
mm,
that it's predicting are going to be slightly
mm,
different ranges, and maybe it learns something more
mm.
general that helps scale transfer across robots, but at least on one robot.
Yeah.
Like it's always going to be better, I think. I think to just
Mm,
go with the robot data. Uh, yeah.
mm. Yeah. Um, cool. Yeah,
Yeah.
exciting stuff.
What
Okay,
did you
cool.
think?
Let's
Yeah.
do it.
Oh yeah. Cool.
Oh,
We
oh,
do it
oh.
again.
I was gonna wrap already. What I think. I mean, I think it's super cool. I mean, I think this human data, ecocentric stuff. Um, but I think, like you said, the accuracy matters a lot. So, uh, you know, I think he basically sounded like he just mostly went with data that he collected from Apple Vision Pro because the accuracy is just,
Yeah.
it's worth paying the price of the hardware because the accuracy is better.
Yeah.
And so I think that's the challenge with like video, just straight up video YouTube data. Like I said, like firstly you need to figure out how to retrieve the video in the first place. That's a huge problem already. And then you know, being able to like based on 2D video, like how do you do the 3D annotation and be super accurate? It's hard to imagine
Right.
that being
Because-
possible if you don't have the hardware advantage that like an Apple Vision Pro.
Right.
Yeah.
Yeah, I mean, this is one of these underrated things that comes out of like the modern, like large scale learning is that it seems like data quality is extremely important too. Like data diversity and quality and like making sure you have coverage of all the tasks you want to cover. And like quantity is a way to those, but it doesn't actually on its own. This is why I'm actually not that optimistic about a lot of stuff using YouTube videos, because like either like a lot of stuff ends up either needing a lot of engineering to get good quality out of them, or they are just like yeah, so if you're doing that, you're filtering stuff out, you're making all these assumptions, it doesn't feel scalable a lot of the time when people do this. And like that's what you see I think a lot with like these robot kitchen kind of I forget the data set names, but eco kind of those kinds of things you end up doing lots of engineering. Yeah, but like and then there's and once if you don't do that, so like that doesn't scale. If you have to do a bunch of engineering just to pull out a handful for like all these different weird cases that arise. And then otherwise, like there's no robot actions, which means that like, and that, like that's one of the whole points of his stuff is that like everything, because we collected it for this and we know that we were tracking the hands, everything is good data, right? Because like we can just take those hand points and put them onto the robot, and that means it works, right? Like not quite, like obviously that's the whole paper, but like yeah, right, yeah. So anyway, yeah, it was a lot to think about. It was a cool paper, but.
Cool. All right, sounds good. Yeah, let's do this again soon.
See you next time.
Thanks,
Bye.
Chris. See ya. Okay.